Oh, that's not the one. Well, let's see if I know which direction to use it. All right. Okay, so yeah, this is the open discussion section, but here are a few slides. So our proposal was, it was a P41 proposal to NIH, to NIGMS, General Medical Sciences, which we submitted in early 2019. And these are some of the main things we wanted to accomplish. We wanted to continue the grand challenges, such as Grand Challenge 4, at least for a little while. We wanted, as has been raised by other folks, to develop or encourage people to not submit predictions, but to submit containerized workflows that would enable ongoing testing, and I'll talk more about that in a moment. Replication, as opposed to these protocol files that folks have alluded to, and dissemination. So if a method works well, then wouldn't it be great if you could download it and use it? Maybe you have to buy a license for some component. But that way, methods that are performing well could be instantly adopted. We also wanted to move to an orders of magnitude increase in the volume and the throughput of the blinded prediction challenges. And I'll talk about how we envision doing that. KELP is part of that already. And then there were major components of training and outreach, which I won't talk about so much now. KELP, you've heard about a couple times. The basic idea is that every week, the PDB releases a file that you can FTP down that has a listing of all the new PDB ID codes that are going to come out about 5 days later, along with the sequences of the proteins and INCHI strings for the ligands, and at our request, the pH of the crystallographic solution. And so what we set up with KELP, we would download that file. And in order to make an easy entry point, I mean, we could just give that file. Anybody could take that and do docking based on that. But in order to have an easy entry point for people who didn't want to do preparation, actually Jeff Wagner, who's here, played a key role in taking that, and basically we blast into the PDB, pull out other existing structures of the proteins of that sequence, and prepare them using some standardized tools. I mean, actually we did it with, I think, 2 different tools, make them available to participants as a download that they could then run docking. And so there's a window of opportunity when they're allowed to put in their submissions, and then right before the PDB is going to release the structures 5 days later, we close the submission window, and we can compare, compute RMSDs and any other statistics we want. And what was cool about this, and again, John alluded to this, is that in the course of a little over a year, this generated about over 2,000 new, essentially cross-docking challenges. And I say cross-docking because the true structure, it wasn't a self-docking. We didn't know the structure of the protein that the ligand was solved with. So this is a true fair challenge. And that was, orders of magnitude, 2 orders of magnitude more blinded prediction challenges that had been held in any of the community-wide efforts, including D3R in the last decade. And this is just in a year. So I'm not sure, these numbers keep changing a little bit. We set up a couple of in-house servers using Glide and Autodoc and Fred, and some of these are in-house, some of these are not. But the idea was we wanted to make sure that if it worked for us before we bothered other people with trying, but there are also several outside participants now. So as of the time of this slide, there were 4 anonymized external participants. And this is just some statistics. This is a number of rotatable bonds in the ligands. This is a histogram, so 5, 10, 15. These are our drug-like ligands. We had a code that would throw out compounds that looked like cofactors or solvent components. And this is the number of heavy atoms over here, and this is a scatter plot of heavy atoms versus rotatable bonds. So there's some ligands are big and some are small. This is just a look at some of the results. The black curves are from the external participants, and the colored ones are our internal ones. What you see here are cumulative probability plots. So this is RMSD in angstroms, so 2, 4, 6, 8, 10 angstroms, and this is 0 to 1. And basically, an ideal docking code would have gone straight to 1. Everything would have, docked with an RMSD, less than 2 or something like that. And you can see that there's a number of methods that are, at least if you don't look too hard, they're fairly similar. One of them is from external, one is internal, and there's one participant that wasn't doing quite as well. But what was probably more interesting in a way, and it recapitulates themes of D3R over a number of years, is how much your results depend on choosing a good structure to dock into. And what we did, I told you that we prepared this data package for people to use as participants. We provided, I think, 5 candidate structures to dock into. So one of them is the protein structure that was solved with a ligand that has the largest maximum common substructure with the one you're trying to dock. So it's a similar ligand. Another one was solved with the ligand that has the highest Tanimoto similarity. So again, these are 2 similar, solved the similar ligands, the ones you're trying to dock. Then the highest resolution structure with no ligand, highest resolution apo structure. I know this is unreadable. Highest resolution holo structure, that's the highest resolution protein structure with any ligand, and so forth. And basically what you see on these cumulative plots is that this is across all of the different methods now, that maybe not surprisingly, but here's some nice statistics, docking into maximum common substructure or maximum Tanimoto solved receptors gives you the best results. Going into the high resolution apo structure gives you the worst results. So there's, statistics backing up something that, I think a number of us have found our way to over the years anyway. But of course, then there's the possibility, as John was saying, of going into more detail in the analysis. So in terms of the proposal, KELP could just continue as it is. It's already doing high throughput stuff. But the idea then was to turn to these, invite people to submit workflows that would run on our system. So we envisioned a Docker containers running on a Kubernetes cluster. This is one workflow. This is another workflow. This is the PDB challenges going in, the predictions going out, comparison with experiment, then a database of performance of the various methods over here that people could then analyze in various ways. What you see here is that each workflow ideally would be modular in a sense that's already been discussed. So this might be protein preparation, ligand preparation, docking, and then you could say, well, this workflow is working really well. What if I try this, try that protein preparation over here? Will that improve it? So what are the determinants of success, at least to some reasonable level of granularity? What I think actually was a little more revolution, I don't know, it's revolutionary, but to me it was kind of cool, was that we really wanted to do this for affinities. You wanted to have KELP plus. That was pose prediction. What about affinities? There aren't enough blinded affinities coming out, to have a blind prediction challenge at this volume, except what we realized is that if people give us the workflows, we sequester them on a server that doesn't have access to the internet and find out what's out there, then basically any new data that get published are blinded, to these guys. They didn't know about it. And so we already curate lots of binding data from the literature. Binding DB curated like 48,000 data from patents in 1 year. So and we also collect, there's also data that comes into Kemble that we can collect. So the idea was that you would have curation process over here from journals. These are workflows that are being fed proteins and ligands that they've never seen before in those combinations. The affinity data flows down here, goes into the binding database for general use, but the affinities come over here, get compared with the calculations, and you're off to the races. So in principle, we would have been able to do tens of thousands of blinded prediction challenges with this method every year if people were up for contributing workflows. Sadly, it was not to be. So this is the, we showed this before, this is where you can take a look at the proposal and the summary sheets, the reviews. And I think, looking over the reviews, some of the things that we thought we could have done better, we could have made clearer that the grand challenges were to continue. It seems like some reviewers didn't quite capture that. Another thing that people maybe didn't capture is that we had letters, there was interest in pharma in using some of the workflows that work best. So here we have an engine for determining what works well at sort of a world-class level. Well, what you want to be able to grab that and use it. People are interested in holding a broader set of challenges. So not just affinity ranking, but what about virtual screening? We do have data on hand to do that kind of thing. And maybe it's worth also mentioning that this framework it's more work, but in principle could be generalized to other types of data as long as there's a data flow to support it. And I think that's my last slide. I don't know if you wanted to finish up with any summary comments, or we can chat about this.
Probably start discussions.
Yeah.
I think just one of the things also struck us in the, okay, yeah, sure. One of the things that I sort of worry about that wakes me up at night or keeps me up at night is this question of whether we're sort of all stuck in some strange echo chamber with regard to the challenges that we face. Because if you read the if you read the summary sheets, they did not seem to really agree with some of the sort of these core challenges that we had distilled. And so I think those are places where, we really need to put a very fine finger on what are the challenges that are really stopping the field from moving forward. Is it automation? Not everybody agrees. Is it more data even? The reviewers also did not agree. They said, fewer data sets. So I don't know. So it's just, we need to discuss this.
So the floor is now open for discussion on any and all of these topics. John, we really need a roving microphone.
So on the point of what the reviewers thought and being stuck in an echo chamber, listening to this excellent technical discussion about directions today, I didn't see how it's going to solve the sort of underlying scientific problems. I mean, to put it bluntly, what's the point in replicating a method that doesn't work? So
you said you're not allowed to say that.
Okay, I did say it. So, and I thought, one of the things that you've already got from the grand challenges is a lot of data to analyze, and you've got the lessons learned on the website and so on, but as far as I know, nobody's sort of sat down and kind of worked out, well, what really are the problems? Why did this one fail? Why did this method do better? It seemed to me there could be more that we got scientifically from the results that are in hand. I should shut up. I'll be offended.
No, I actually think that was one of the things that came through to me was, well, where's the science? As opposed to a lot of plumbing.
Perhaps it's just that we assume that most of the folks here have a good handle on what the scientific limitations are. We know force field sampling, the treatment of chemical effects, all of the steps in a preparation pipeline, which may or may not cause the calculations to be sensitive. So maybe we need to be clearer about that. But what replication enables is for you to explore each one of those questions systematically. If I use the same method as someone else, except for the protein protonation step, and if I can't easily replicate their work and look at those differences and compare exactly how that choice impacts the output, then there's no way that I can make progress unless I duplicate all that effort. And if everyone is duplicating all of the effort all of the time, we're going to get nowhere. So I would say there's a direct reason that we need to be able to replicate particular parts of the.
The technical discussion was really great today. I think these are super ideas, but I think that's half the picture, and the other half I haven't heard much about. There was a bit about it in sample, but not so much in D3R.
So let's say through your automation, you find there's a discrepancy between force field A and force field B. One's on the top, one's on the bottom, and then there's a few in the middle. Okay, now what? How do you improve that science? What's your way to deconvolute what is the contributing factor that's involved in your MD simulation that's being driven by that force field? How do you generate from one to the other? Or do you just adopt the best one in that case, and then, but what if 7 weeks later or 2 challenges later, the order reverses for that system? What do you do? How do you extract it to learn?
Do you want me to? Okay, I'm gonna take those. I think, yeah, this passive 100%.
I think from my point of view, actually we do a lot of cross-validation of different methods. So we do read other people's paper. I mean, although I talk about mathematical machine learning, actually I try to reproduce everybody's work. That's true. And in the past few years, we basically could write 10 more papers if we don't participate in this grand challenge. We spend a lot of time doing other people's method and try to see which method is better. But particularly, we wanted to see if that method can improve our method. things like that. So we put a lot of attention. So I think that's why we think this whole thing is really make the whole the community actually make a progress. So not only from my point of view, I also see other people, they also make a lot of progress. That's why you see in this year's competition, and the people have a fraction win instead of typically in the past, one group win, everybody wins the every category. Now we see a bunch of people win a fraction of stuff, like what I put in my talk. So what it means, when the people are catch up, everybody has basically learned what is going on, and then different methods somehow converge over there. Those is the point nobody mentioned about, but we do know there's a convergence over there. Different techniques, they actually perform quite similarly. So that's why we also first time have a force field based method is also able to win something. Typically in the past, only machine learning. That means all kinds of different methods, they're actually getting converged. So this is really the things I think the community actually want to see and want to encourage and actually basically achieve the purpose. That's the way I see it.
I think one point I want to make is that I think this challenge is really good to test kind of those workflow and all those things. But on the other hand, like the John made a question is, I think the main question is like through this challenge, how can you further stimulate the further innovation? So how to stimulate further kind of develop new methods and all those things. So this is something that's also related to the comments is maybe is from those past challenges, how can you organize those data you already have to provide those benchmarks for people to develop new methods? So then when for those people want to develop new methods, so it's not necessarily, when you develop new methods, it's very difficult to develop container, develop protocol. You really try and error, but if you have a kind of really establish benchmarks there, kind of you through this, kind of you can always update that and also make like those workflows for those data set to develop new methods easier. That's maybe this is kind of to stimulate further innovation. Maybe that's a point also need to make in the kind of grant revision.
I mean, one thought I have about that is something that John said, which is that, to the extent that, one lab isn't developing an end-to-end method, but maybe they're developing a better solvation model or develop charge model, that you stimulate innovation by letting them plug that into a workflow that then will let them test the whole thing as a, yeah.
There was also the general comment, another general comment that when we were discussing with the program officers, they also reiterated, was also the notion of whether actually forcing people to do this type of automation actually dampens innovation, because it's this, unless you're already sort of into it, there is quite a sort of an activation barrier or energy that you have to invest to get your end-to-end workflow really fully encoded. So it sort of maybe cuts against it a little bit, but.
I think that what the reviewers need to appreciate is that the grand challenges, D3R, is firstly, it's addressing a show-stopping problem of having known areas of error convoluted. This is a point that Ben brought up a few minutes. And so just being able to deconvolute them enables us to work on something. A second point is, again, Ben's question, so what do we do? Well, I'd say in terms of best practices, another outcome of the grand challenges is it gives the community an immediate best practice. In a sense, in a kind of a crude way, you can say, whichever method won the grand challenge, that's the best method, use that one. Like in terms of a straight readout from the dials. A third benefit that it offers is it gives all the developers a clear relative ranking that they can work from to try and improve their methods. So that's a stimulus to the community. Maybe the person who won the challenge can sit back on their laurels and do nothing, right? But everybody else, they know what they have to do. In the area of the, again, Ben, sorry to pick on you, but you raised the specific area of force fields. So what do you do? Well, it's interesting. It's a very specific message to the force field developers that they've got a deconvolution problem of their own. They've got to figure out where the problem is and to improve it. And it allows them to tell them when they have improved it. It gives a clear benchmark for improvement. So I see all of these as kind of orthogonal stimuli to the community. And I would personally benefit from them all, and I think most of us would.
So I agree with what people have said, and also to me, I feel that the thing I really appreciate D3R is. You usually see people claim that in the papers they did very well with some data sets. But then when you really apply it, then you found that it's not as good as they said. So D3R gave us a very good blind box for us and also real practice for us to test the things and help us improve the results. And also, as Guo said, we can learn from others too. So this helped the whole field move up. Just considering our accuracy for the post prediction, the first time I remember like 2 is pretty good. Now you have to go to below 1. So I know actually 6 groups or around 6 groups or 7 groups, they are below 1. So I think this improvement was obtained through the help of D3R. So hope that maybe you can write that in. And also, so regarding the large data, small sets, and so we have 2 parts. One is the grand challenge, so that addresses the reviewer's question. So you will continue that. And for the this workflow thing, I think the best thing for it is that it forces people to do it objectively, because otherwise people can always do manual vision, so which nobody else can use. So for people, particularly for like simple users, they really need those automated things rather than the subjective input. So you already wrote here, I feel one of the reviews raised a good point. Novel virtual screening is maybe that's something you could do. So another thing I'm thinking about is, so one of the reviewers raised the question about how to compare and analyze the data and also provide helpful input to the reviewer, to the participants. So one thing we could do maybe is, right now there are 2 parts. One is sampling, the other is scoring. So right now we only get the results. So we don't know whether it's really because the sampling is better or scoring is better. So if maybe we could learn from Capri, like add a second stage. So basically everyone will have to use the same sampled conformers or poses, but then see who can pick out the good ones. So maybe that provide a way for a very objective comparison, also helps people to pin down their problems.
To get back to John's point about how do we really make progress in the science aspect, part of what we're trying to learn is how things can fail. Right. So as our understanding of the different modes of failure that are common to different kinds of classes of methods evolves, this is another reason where the standardizing the assessment part of the pipeline could also look deeper if that data was exposed and look for sampling failures, look for slow conformational changes or ions or waters getting stuck in binding sites, as in the host gas systems. So the more we understand and the more we codify and the more we standardize, the less time we have to spend worrying about the same modes of failure that we know about, and the more time we can spend exploring modes of failure that have yet to be discovered.
Right, it's a little bit of a sort of easy kind of ad absurdum point, but that's a really interesting thing you mentioned about conformers, because the logical extension of it is to break down the competition into, hundreds of sub-competitions. Yes, protonation is a problem. Yes, where does water go is a problem. Yes, conformal generation is a problem. If everybody was running on tiny, tiny little chunks of the whole problem, then the comparison sort of comes out in the wash. I know it'd be deeply impractical to run, but maybe just a thought.
I think one of the things that's important to maybe be explicit about is the two communities that we keep talking about. And, sometimes we talk about pharma versus academia. I'd like to think more about, science and innovation versus application execution. That's maybe just because I don't like being labeled as industry because it sounds boring, but sorry. And I think both communities need to think about how to be very explicit about what they need. And, it tweaked me when I read in some of the responses that, it doesn't address the challenges of the field. And I'm like, well, what do you know about the challenges in our field? Because then they don't articulate what they see as the challenges in our field. And at the same time, I think, this all started, when was it, 2005? And, that was a 2-day discussion where a number of people really sat down and articulated, okay, really, what are the challenges for drug discovery? And I'm not sure we've done it in that depth. And so that might be something, because personally, when I saw virtual screening being raised, I'm like, I'm not sure I would call that the biggest challenge for drug discovery, right? But that's maybe just me. So I think on the part of execution and best practice, I think those of us in drug discovery maybe need to think a little bit deeper on really articulating what the biggest challenges are for us. And as an aside, the best practices thing, yes, technically the one who was scored highest is the best practice, but then if you look at it, the same docking engines were used in the top and the bottom, and so I still cannot actually use that as an execution person. On the academic side, the innovation science side, I think we as a community need to think about what are the data sets we need, and that the challenge with the way, the high throughput proposal is that you're still just going to get what comes through the pipe. And I think being very explicit in how we do the design of experiment and really say, what does your best data set look like? If you had unlimited resource, what would you like it, how many ligands do you need? What's the distribution of physical chemical properties? How many stereoisomers, regioisomers, and to get to those points of, can you really drill down into some of these characteristics? So I think as a community of scientists, can we be more explicit about asking for what we want? Because some of it we might be able to get, right? And maybe that also becomes part of what you ask funding for, because there are a lot of molecules that are in patents, and if you couldn't get them from the company, you could get them resynthesized, and you could just screen them and get properties, because that is one of the big challenges, is the multi-objective optimization, right? So can you get data sets that don't just have the affinity, but have a selectivity component, have a solubility component, et cetera? So I think that's... Might.
I just wanted to mention a challenge that I didn't hear about today that's really important. As I've traveled around and talked to many people doing drug discovery in pharma, a recurring topic that comes up is they want to know, what is the robustness and reliability of a method. So it's implicit in a lot of what we do and what we talk about, particularly in the free energy calculations, but something that isn't explicit yet. And I just want to formalize it here, is to be able to know when you can apply the tool and expect a useful result from it. So it's a tough one to make a challenge and to test, but that's one of the things that people really, really want, and that would change the application of drug discovery in industry. Yeah, I agree with that. I think that one of the things that both Cameo and CASP has done is to test how well people can say for a particular prediction what the accuracy is. So if it's protein structure, both locally and globally, how accurate is that case? So you're building a model, you have some idea how well the methods work. And in CASP, we put a major emphasis on that. We have a section on it. And in that way, people have developed methods. And from a user's point of view, what's the use of a model if you don't know how accurate it is? But if you can say, this loop, I don't know where it is, but this active site I'm really sure of, it is important. And I think the same thing applies here. And it's not just a sort of general reliability, it's for that particular number, how reliable is it?
All right, I have a couple points to make, and I'll try to see if I remember them all. First of all, I really like the idea of kind of codifying your thing. I know there's a big barrier to it, but one of the things Stefan didn't really well in his presentation yesterday say, oh, we did all this work, we have a new method, let's go back to sample 2 and retry it, right? Had that been codified, every time you submit a sample, it's like, let's go back and do sample 1, 2, 3, 4, 5, 6, or 5, and now also 6. And we could have seen, like, wait, it works really good on sample 6. What the heck happened with sample 2? He wouldn't have to go back and do the retrospective because it would just happen automatically. So I really do like that effect. And I know I've talked to John quite a bit too about, for sample, now that they got funding, is don't just rely on the academic labs to give you what they want to make, go buy the stuff, right? There's enough CROs for chemical compounds, for measurements, to go buy it. Ask for that funding. It doesn't make sense to be at the graces of the academic labs. And in some ways, it doesn't make sense to be at the graces of the pharma companies saying, hey, yeah, BASE is not a project we're interested in anymore. Let's dump some structures to you guys. Because it is interesting. I'm not saying it's not. But at the same time, for sample, people actually didn't do very well for a while. Because the challenges varied so much in difficulty. Could we do something simpler for protein ligand posing to say, how do we make it a little bit more challenging instead of just driving all the way between things we don't really know much about? And so for sample, one of the things we recommended to John was to say, okay, let's try to make simple compounds with charges. It's one problem. It's not 10 problems into one. And so I think maybe we could learn something from this. And then I'm going to be a little controversial and say, don't hate me for it, but docking engines have not gotten better in 10 years. You guys have all figured out how to work around them, right? You've figured out how to pick the best templates. You've gotten good at data mining. You've gotten good at modifying the scores you're getting by some tweak factor. It's a little bit sad to see the docking engines have not really gotten much better, but it's not like, I work at OpenEye. It's not like Fred has gotten love in the past 3 years or 5. So we're not exclusive to this, but at the same time, it seems to me like you've all gotten really good at data mining the PDB and then working around the docking scores. It's not like the docking scores have really gotten enough attention. And I'll leave it at that.
Thank you. No, actually, I mean, that was working. This is one of the things that I think we were commenting on, is that, I mean, one of the things I think came clear in the early challenges is that people who were able to make good use of the available information were succeeding. And so, in a sense, that meant we didn't know how good I don't know what this thing is doing. We didn't know how well the docking and things were working because different people were working from different baselines. In a sense, somebody could use a really great docking thing, but if somebody else was more clever about using the available information, they would look better. So even if in a sense that's not what we want to be doing, we'd better be doing it so that we can compare methods on it. You don't want any unforced errors in a sense. Yeah. But I mean, I think people have really gotten better at that. There are a number of really creative ways of using that information that came through in the talks.
Just to follow up to what I said before. So it's not that we don't use workflows. We do use workflows a lot. We'll take like an MMGBSA. We'll use all our force fields that we have. We'll use multiple shells. We'll use all the protein crystal structures that we have, and then use and see which ones build the best models with the first 10 compounds that we get. But the part that's unnerving is one day this force field works great, and then you'll do like 3 projects later, and then that one's always the worst, and this other one that you thought was garbage from before works the best. It's sometimes pretty unexplainable.
Maybe it's a comment for you or other people in the room, but reflecting on all the past grand challenge, and giving a big overview on success and failure. Can you say, do we understand what data set do we need to validate methods? Do we even know how much bigger they should be or what they should contain? Or can we classify the source of failure? Or are we still at a stage where we can't really learn from the different data sets?
I have some very strong thoughts on that. Now, it depends on exactly what we're trying to do. If we want to predict the accuracy in a real-world use case, then we need a data set that is representative of that and probably very diverse statistically so that we can answer that question either in a statistical model framework where you're trying to predict how well it's going to help you maintain potency of a highly potent compound in a particular target class, or if you're just trying to improve a crummy hit, that's going to be a different kind of data set that you need to actually compute that performance. The machine learning world is finally getting to learn this by how they do cross-validation of very large data sets. Like if you leave out an entirely new type of scaffold, and you try to predict the out-of-sample scaffold, it might give you some indication of how well you will perform in the case that you're switching scaffolds. So I think we need to do that kind of exploration as well as the exploration of different data sets that isolate individual challenges so we can learn about the science. But there are very different kinds of data sets that are needed and very different kinds of things that we conclude from them. It's not just like every piece of data is equally good. I love the KELP++ idea, but the idea of just feeding random data through and then trying to slice it later to learn something is a little bit scary to me because we don't know a lot about the quality of each of the individual kinds of data that go in there, and then trying to extract expected performances out of that seems challenging. Had you folks thought about how you would, like, because you've BindingDB is full of all of this stuff. How do you ask questions of it that are sliced towards particular ideas or applications once you have that kind of data?
I mean, things like, if presumably if there's an affinity calculation, there was somebody, well, I mean, the thing is that this thing was so open-ended that some of the predictions could be machine learning and not be structure-based, and so that you look at those a certain way. But then the workflows would have access to a local representation of the PDB, so those would be able to do structure-based. And so you could look at things like, things that everybody talks about: how hydrophobic is the binding site? Is there a metal? What's the resolution, and also how much background data are there? Is this something that has never been encountered? It's a new target or is it an old target? And so, both, I would think, using some intuitive suggestions, but also almost by observation, you should be able to discover, well, all the methods are failing on this protein, what is going on, and go in and try to do some analysis. So I don't think we went into enormous specifics, but it seemed, yeah, that's a good question. I was at a number of years ago. I was at Kitty Hawk, I guess, North Carolina, and about how they made the first airplane, and they were fooling around with the shape of the wing. So I guess the Wright brothers were fooling. They didn't know what was going to work. They didn't have a model, and I sort of feel like a little bit like that's where we are now. I mean, to some degree we can do the analysis, but to some degree, it's a lot of what we do is empirical. So some of the neural network methods have really been doing nicely, but who knew that they would? I mean, maybe the developer knew, but I don't think we knew. I think to some degree, what these challenges offer is a laboratory for doing experiments to see, because you don't know what change in the method is going to turn out to be key, and also you don't know how many tune-ups you need to do to get all the errors down so that it's not being swamped by some bottleneck error.
Yeah, so a couple of things. First of all, to Mike's point, in a very interesting book, Anti-Fragile, and Nassim Taleb, for people who haven't read it, is excellent. And he makes the argument that pretty much all breakthroughs have come from this tweaking process. He uses the airplanes, but if he looks back to a lot of really good ones, and then scientists always kind of try to rationalize and build this beautiful theory to explain the thing, and then say, look, we got this beautiful theory. But most of the big breakthroughs do come from just defining the problem you want to solve, such as flying a plane, and then just putting a lot of people at it and tweaking and tuning and letting nature kind of tell you what the answer is. So I think there is a huge amount of value to that. So that's great. And I think one of the real problems and kind of the elephant in the room, as far as I see, is the docking challenge. I think the slide that you put up, Mike, showed 20% of the cases less than 2 angstrom. I mean, it's useless. And all this free energy stuff and all the base, for example, it was like an overly trivial example, right? Because you can just map the macrocycle core and then you could get a 0.25 angstrom RMSD. Nobody can get 0.225 angstrom RMSD for anything real. So I think that kelp challenge is fantastic. And I think it just establishes, and people say, well, better scoring functions and everything. We don't have dynamics or any flexibility in any of the docking. So no scoring function can fix any of that. So I like to kind of put it out there. I think a lot of academics don't work on docking because it seems like it's kind of I don't want to say trivial problem, but like not a rigorous problem, because historically it hasn't been a rigorous problem. And now I think we're at a point where we could actually run free energy simulations to do docking. We can sample, and in the real world, when we're in drug discovery and we have a novel target, it generally takes a long time for us to get a crystal structure. We're often working from homology models or APO structures. If we do have a crystal structure, it's probably from a competitor, so we can't work on that chemical series. So we're almost by definition having to find novel chemical series. And if the docking accuracy is 20%, then everything downstream is going to be useless. And that's, I think, really probably the biggest challenge that I took home today, is that rigid receptor docking is pretty useless in prospective cases, and that would be a great area to work on. And we could still simultaneously work on the free energy methods, assuming that we can generate reasonable poses. But without having those two pieces together, there's not really going to be anything useful in the real world.
Thank you. I really didn't know what to make of the kelp results. And so, I mean, I guess there are a lot of people in this room who have a lot more experience with docking than I do. So does that seem like, well, it's just too hard because it's too automated and it's cross-docking, and those are not representative and those are worse than you would expect? Or is that pretty much in line with your experience, people who know whoever? Okay, I see a hand.
It is absolutely what one should expect for cross-docking in general for a rigid receptor, and it's not clear that flexible receptors will help us at all. If you design a truly good cross-docking data set, this is exactly what you're going to find: 20% success rate on average. Now, sometimes depending on the data set, so for particular protein classes, you can get higher, like kinases, you can get up to about 30% success rate, but across all protein classes, 20% is the success rate at 2 angstroms for cross-docking. And so it's not, I liked your data because it replicated numbers that we've seen and known for a long time.
But then I guess it gets back to, you know, what is needed for drug discovery, which is not just that initial result that comes out of your, you know, blind docking workflow, but it comes from looking at the SER you have and figuring out, you know, what are the key interaction points in your series of ligands and being able to tweak it from there. So I think in practice, in drug discovery, it's better than that, right? So it's the automated part where I fully agree that is what would be expected. But in a drug discovery setting where you have an SAR series, you can work around it, and then yes, you look at flexibility, you do all kinds of other things. But so it gets back to what really is the big problem for the execution part, and what is the big problem for the scientific part, and really understanding ligand protein interactions and how to model those. So yeah.
I think that's true, but certainly for I know I'll stand in the middle. For the people in this room that are developing methods and focus on free energy methods, by far the highest value comes before you have a structure. If you can get it right, you know, once you have a structure and a bunch of SAR, a lot of these machine learning methods will start working very well. QSAR models will probably work pretty well. Pharmacophore models will work pretty well. You will complement that with a free energy prediction, but the project will go forward once you have SAR, whether you have a free energy method or not. But prior to getting that structure, everybody's in the dark, and I think that's, you know, a really super high value application of free energy methods. And it was mentioned by several of the machine learning people, you know, very clearly today, is that like once you have this data, it's great, and these free energy, you know, these physics-based approaches can really shine when you don't have data. But the results, you know, the KELP challenge, you know, shows that when you don't have data, you know, they don't shine. But it's because nobody's using free energy methods for docking. You know, people are assuming you have a pose and then running free energy calculations. But why not be running more rigorous calculations to get a pose? Absolutely. Yeah. Yep, that's right. Yes.
So while I would like docking programs to have higher than 20%, one of the things that I do like to keep in mind, I mean, the reason we're seeing performance improvement is exactly like has been said. It's knowledge learning. People are basically mining the knowledge, the prior knowledge. X-ray crystallography did not go exponential until the Structural Genomics Consortium happened, and we acquired enough novel folds that we didn't have to solve structures de novo. We could use molecular replacement. And I think the same thing could happen here. If we actually had the ability, if you will, to acquire more prior information, so maybe if we had chemogenomics probes or whatever, so we have prior information, then we don't have to solve the fundamental problem. We can bootstrap with the knowledge. And it might be important to point out that, again, structural biology didn't explode. It didn't go exponential until enough investment happened that there was a data and knowledge that people could build off of, so that improved the efficiency.
It's a great suggestion. It would be interesting to see how much data would be needed, because for proteins, you have 20,000 of them, and that's it for the most part. You have, you know, a few hundred, maybe a few thousand folds, and that's it. And so once you enumerate that, you know you're in very good position. The big question would be, for protein ligand docking, how many cases do you need to really have enough?
Based on the numbers I saw, it would cost about 2 trillion to have all the enamine compounds made. So, you know.
Not just the tip of the iceberg.
That's right. It's either that or Greenland, I think. I guess the other thing I was sort of wondering is, I mean, so for John, and do you have a sense for the scope of protein ligand things that'll be happening in sample, or you want to comment on that?
Sure. So the current the current planning is to continue to develop model systems so that we can field 1 or 2 protein challenges with the idea of doing iterative versions of that. And as we heard yesterday, we're working on trying to develop HSA and NanoLuc and maybe a couple of other protein systems down the line. There's a few other things that are synergistic that might provide more coverage, right? We've obviously are going to continue to talking with the D3R folks about whether we might be able to see if we can somehow expand the scope of sample or somehow cover the gap in protein ligand stuff for the next year at least. And there might be ways to do that with NIH supplements. We'll talk about that strategically. There's also synergistic efforts where David Hahn, I think, is here, who's the new open force field postdoc working at Janssen in Belgium, and he's going to be curating protein ligand data sets for retrospective evaluation. That's part of our charge for the pharma partners interested in having an open data set that's not just 12 systems that work for Schrodinger. So the idea is that they will contribute data that they can extract from their own institutions, and if they're doing that anyway and going through the trouble, we might see if we could field a blinded challenge or help field a blinded challenge with those data sets that are cleaned up and then submitted for holding in a retrospective or before they go into this retrospective data set. So there might be ways to capitalize that too. We're also still talking to NCATS and Diamond MX, XChem to see if there are other ways we can expand. They are shooting a lot of crystal structures at Diamond MX, and they have the idea that they want to get the most value out of this as possible. So there might be ways we can again synergize with that and maybe the chemogenomics efforts that are going on there to get more data liberated. But it's we're hitting up people with a tin can and begging for or tin cup begging for data at that point.
So one question that maybe we should think about is expectations, right? So what constitutes progress? What do we expect? If we do this 3 more times, right? How do we know that we gotten better or not? Against random, more or less. The example, John obviously spearheaded this, right? So CASP has been doing this for 25 years, and this last year suddenly, boom. There's a big change, right? I mean, there were periods of 5-6 years where nothing really interesting happened. So I think the challenge is to convince NIH that the question is still relevant, that something like this is about the only way to go at it, and the people in this room, if we cannot solve it, then we basically need to figure out that there is an alien technology and there is some dark matter thing that we don't know about, right? I don't know how to do that, how to convince them. But I think that's the goal, right? That's the idea, that it's a problem worth doing, worth attacking, and this is the right set of people to do it. Maybe it's not, but I don't have any evidence that it's not, right? So what about expectations? I mean, what do you think it's progress, right? If we come back next year, what does it mean that people got better? More people got below 1 kcal, or what's better, right? Everybody got a kcal per mole better, or more people got below 1 angstrom? What's progress?
Yeah, that would also be my point. I wanted really what was the origin, why sample was successful, and why D3R actually was not successful in terms of getting funded. And the interesting thing about that, I can talk from a German perspective, is that very likely you ended up in a life science community of reviewers that felt to some point, that was at least my impression, even offended by the assumption that technology alone could solve the biology problem. So because that is exactly what I'm hearing, and that is the reason why I try to avoid the life science division with the DFG at all cost, because exactly of these questions. So going to model systems, well-defined model systems, where you can really try to understand the physics, the chemistry behind these elementary interactions, could be more fruitful. That would be one way. And the other thing is, I think that one should really take reviewers very, very seriously. And that means one of these suggestions was to team up with medchem guys, with somebody with real first-hand experience with the drug discovery project. And that means really working together with the guys whom you actually have to convince that the methodology is useful. So my personal experience talking and working actually with medicinal chemists and even with people from a medical faculty who try to really bring something close to a market, or at least convince the community that, for instance, a certain kinase inhibitor, if you repurpose one of these first generation back to a new kind of disease makes sense. They just want answers for their target, and that's it. So nobody of these guys actually cares about anything about the generality of the methods or the automation of the method for a broad variety of problems. They have this target, and if you don't work with that target, they simply are not interested at all. And I think that is my personal, experience. But maybe it would be a good idea to be just more ambitious and really try to extend the whole supply chain by not only keeping within this computational range and establishing models and methods within the computation alone, but having some sort of feedback loop from a real world drug discovery project back to the method development.
Yeah, I wanted to chime in, I think, on Adrian's point about progress, and maybe I'm speaking as a former kind of docking method developer. I was really struck by the vision of getting a pipeline and a workflow where we can interchangeably exchange sampling, scoring, ligand preparation, and so maybe as a in the spirit of crawling before we run, you could state a goal of something like the data table you'd like to have as a goal in next year's. We'd like to have the, say, 3D matrix of ligand prep, scoring, and sampling, all against all, for a particular set of systems. It doesn't necessarily mean at the end of that you would have a method that necessarily performs better. I think the goal of generating that data set would be to find the sweet spots, hopefully, in those intersections. There are probably some docking methods that work well because they sample very selectively and allow a weaker scoring function to do fine, and vice versa. And I think we're empirically hazarding our way through that phase space, but I don't know necessarily. So I don't write grant proposals, so this is. I don't know necessarily that wins the argument with the NIH, but I think the concept would be that's a foundation that you can then provide to methods developers as a community, and that at least gives them a framework to start thinking about how they design their algorithms a little more systematically, maybe. But.
Thank you.
Yes, so I guess one thing, which I guess perhaps could be stressed out, right? If we have to focus, to address the innovation part, could be, for example, it was nice that this round there was actually macrocycles, right? And there was basically the macrocycle hype. It's I guess not very clear at what stage it is, but definitely a few years back it was pretty high on the line, right? And I guess part of the reason, right, why we have this data set right? So, but basically perhaps to articulate that actually that this, for example, in the grand challenge part, there would be not the classical simple docking, but actually something which is actually interesting, in pharma, for example, say macrocycles. Right now, I guess another hot thing is products, for example. So trying to have this, of course, it's not just ligand docking, it's also protein, but maybe somehow to focus that basically it will be focused on the new class of interesting compounds and everything, because because then it could address the innovation part, because that's part of the things. I mean, like, it also relates to the method development, right? If you write an NIH grant and try to say, okay, I'm trying to do a new docking method, basically, I mean, like, until recently, it would be just basically like going nowhere. You need to say, okay, I'm doing some new class of things, right? I mean, like new class of compounds, and that gets interesting to the reviewers. So perhaps kind of to say that, and as I said, in a way it happens naturally, because the data set, if it comes from pharma, it actually comes from something what is currently kind of hot, right? So or was hot kind of few years ago, right? So it could be perhaps somehow played around to say that actually that there is this new interesting modalities and things like that. I don't know if it's helpful, but to me it sounds like it could address some kind of this innovation issue. So.
Thank you.
I guess on that topic, and also, Stefan, your question about, why one is successful and one not, and so forth. In as much as grant proposals often seem like just rolling the dice anyway, sometimes. Yeah. Yeah, this is, I think, certainly, I think Mike and I can acknowledge that one of the issues perhaps that we did not anticipate as well as we should have, we applied to a very specific type of funding mechanism, which is called a P41. The advantage of doing this is that it is supposed to be community serving. This is certainly a highly community serving event, obviously, activity. It's much different than the R01, which is the research-oriented work that Mike and I do in our own labs. And so the P41 is designed to do this. And it also has a substantial portion of the funding also can go for training and so forth, which also has been established in the community as being, an interwoven sort of big need. So we saw that as being more attractive than going for an R01 type mechanism, which is, I believe, how Sample has been funded. So, and also to this point, so for these P41 panels, they are predominantly experimental life scientists who are developing new microscope technologies and so on and so forth. So there's, if there's 12 people on the panel, maybe if you're lucky, 2 will be computational. And so you really have to make these arguments to convince them that this money is going to be worth not funding the next great microscope advance. And I think maybe we did probably, as came out in the reviews, I think the impression from the panel was also that we focused a lot on you all, essentially, on the method developers and the benefits we would bring to the innovations to your methods, instead of saying, look, if we enable this technology, we can maybe make the next anti-cancer therapeutic in collaboration with Novartis or this particular academic group. So it gets a little bit, I think, into the technicalities of sort of the grant mechanism itself. And I think, it's just a matter of how we chose to spin it. And we had kind of convinced ourselves that it was going to be successful, but obviously, we failed miserably. But in any case, that's certainly part of it. And it also speaks to, Dima, I think your point about what is sort of the new sort of actual scientific output that comes from it in terms of either a chemical advance or a biological advance for the NIH. Oh, back to you. I wish we could toss this thing.
And another aspect, I don't know whether it was just one of these reviewers was about this virtual screening thing, or was it 2 reviewers who brought up that point with the lack of virtual screening? Okay. Yeah. Maybe this reviewer meant something different, because my impression was that the idea is that one should pick up the growing area of generative chemistry, right? So we heard that this morning, and I mean, this is a mega topic, At least what I know from Bayer and from Sanofi, right? This is a mega topic. So people try to figure out to walk into chemical space and to find the right generative adversarial networks to really, well, get the correct pathway where to go. And then the point is, all that happens basically on a purely virtual level, right? So what people do, for instance, with the autoencoder or the decoder is you train a network against empirical log P, right? Or empirical whatever property. So the point is, if you really want to be successful with one of these generative chemistry things, then the prediction quality has to be at least as good to allow for going systematically into a way to really optimize your properties for a given class of targets. And I think this is one of the things that goes hand in hand with all these efforts that are intended here in this community, right? Because all these methods are actually necessary to be developed to a point to be applicable to such of these GANs, right? That would be.
Just to follow your point, can you change the grant into R1 or something like that? Oh, I see. Yeah, I also remember there's a cryo-EM. I mean, a couple of years ago, they also get a grant renewed, and they also for community standards corrections, things like that. I mean, PI was washu. I mean, easily went through the panel. No problem at all. I don't expect things like this. And actually, I don't think they did so much service like you did. Or cryo-EM for cryo-EM technique. Yeah. Yeah, yeah. Yeah.
Does D3R need to be funded by NIH? Do you need funding from NIH, or can't you work directly with industry to keep things going?
Well, I mean, that's up to industry. How much money was this grant?
It was 800,000 direct cost. I mean, the current grant is 500. And I'm trying to say, I mean, I feel like it's pretty efficient. Oh, sorry. So the whole effort that we have had going for the past decade has been 500,000 direct costs. So that's like spendable dollars, essentially. What we had proposed was filling a budget of about 800K. But you know, you have more expensive folks doing software development and doing a good job with that, and so on and so forth. But you know, one could think about what's the minimum budget, you know, and so forth. One would need to really do it. I would say probably not less than 500,000 a year, realistically. And that's getting data from external folks. Yeah, right. Like that's just the shop aspect of it.
Well,
all right.
Well, thanks everybody for the really interesting discussion. Thanks so much for the great discussion and all the interesting points. Do we have anything we want to say, or are we just gonna? Well, I think we have a picture of a sunset. No, I think we're set, right? Okay, well, thanks everybody. I mean, I certainly had a great time at this meeting. I hope you guys had a good time and learned something. I think one thing I don't know, is Megan here? She's probably headed out, right? Okay, well, she did a great job.
I think we should all thank you too.
Okay. Thank you. So the meeting is adjourned, except for the SAB. Okay. Enjoy La Jolla. Enjoy La Jolla.